Thermodynamics is the branch of science that deals with heat and other forms of energy and how they're transferred among systems. So with thermodynamics, we're going to look first at the laws of thermodynamics. First law says energy is neither created nor destroyed. It's also kind of a way of providing a way to keep track of the energy as it changes form. So when we looked at entropy in a previous video, we noticed that entropy, it changes. And so it's all about the pressure, the volume, the temperature, the moles, that kind of thing. But how does it change whenever you supply energy or take it away? How does energy change between those two? Because it's not created nor destroyed, it's just simply changing form. So it's a good way to kind of keep track of how we're making those energy transfers. And that's the idea behind the first law. The second law is the idea that total energy is constant in the universe, but entropy is always increasing in the universe as a whole. Does that mean we can't have a decrease in entropy for a system? No, because the universe is simply the system plus the surroundings. And the idea is that for a universe, for everything that we've got in this world, entropy increases. We increase toward disorder because as time passes on, we're getting more potential places where energy can move, matter can do. We're increasing those microstates. And so entropy is always increasing for the universe. And it's important to note that your system and your surroundings add up to your universe. But for a spontaneous process, there's always an increase in entropy, at least for the universe's perspective. And then last but not least, the third law of thermodynamics, and that tells us basically what a pure perfect crystal could have an entropy of 0 at 0 Kelvin. And so we're kind of establishing this as a standard because we know that gases have more entropy than liquids, which have more entropy than solids. But is there a perfect solid that might have no entropy? And yes, there is, but it's theoretical because it's a theoretical perfect pure crystal. So no defects, absolutely perfect, but then also no energy, 0 Kelvin. Okay, and so that would be the only way where we would have no entropy for a system. If not, our entropy is always going to be positive or negative, depending on if we're having entropy losses or entropy gains. So in order for us to discuss thermodynamics, we really needed to be able to discuss Gibbs free energy. Gibbs free energy is G. Delta G is change in Gibbs free energy. And so Gibbs free energy, just like enthalpy and just like entropy, is a state function. Remember, a state function is something that only depends on final and initial states. That's why your delta is change. So it's final minus initial. We don't care about the pathway that's taken, so that's a state function. We don't care if you took the stairs or the elevator, all right? It's just final state minus initial state. And so Gibbs free energy is really the big fundamental variable of thermodynamics. It allows us to relate enthalpy and entropy to determine the spontaneity of a system. So the symbol, first off, you see the little degree symbol. In this case, it denotes standard states, which are 1 atmosphere, 1 molar, and 25 degrees Celsius. Prior, when we were talking about gas laws, that was when we were looking at 0 degrees Celsius. But for this case, we're looking at 25 degrees Celsius for standard states. Gibbs free energy is going to be the only variable that's going to absolutely predict spontaneity of a system. So whether or not a reaction will proceed without an input of energy. And so if delta G is negative, it's spontaneous. If it's not, and delta G is positive, then it is non-spontaneous and you have to give it energy for the process to occur. Enthalpy and entropy are predictors of spontaneity, but they're not the last and final choice. That's Gibbs free energy. If Gibbs free energy is negative, it is spontaneous. If it's positive, it is non-spontaneous. Enthalpy and entropy can predict spontaneity, but depending on how they are in relation to each other will determine if the overall process is spontaneous or not. Let's look deeper at that mathematically and figure out if we can't discern the correlation between the variables. Before we get further though, we've already defined entropy in a prior video. Let's do the same for enthalpy. So delta H is the change in heat flow. Remember, endothermic means it requires heat. Energy has to be put into the system, and so therefore you have a positive delta H or a positive change in that energy that is heat. Exothermic means you're giving off heat, so it is a loss of heat, which is a negative change or a negative enthalpy. All right, so here's our big equation that we're going to use a whole lot in this chapter. Our Gibbs free energy equals enthalpy minus your temperature times your change in entropy. Now, of course, all your units are going to need to match, that way they cancel each other out. But let's look at these overall. What lends itself to spontaneity? Remember how I said enthalpy and entropy can predict spontaneity, but it's Gibbs free energy that determines overall conditions. So, in order for a reaction to be spontaneous, delta G must be negative. Positive changes in entropy are going to be predicting spontaneity. Okay, so if you have an increase in disorder, the universe desires that, therefore you would think all positive entropic increases are going to predict spontaneity. But that's not always true. Okay, but positive delta S means, I think it could possibly be spontaneous. And then similarly for delta H, if you have a loss of heat, that means heat was not required for the system, so therefore I did not have to act on it with outside forces. Therefore, I'm going to suggest that a negative delta H is going to suggest spontaneity. Mathematically, if we put these into our system, we can see that this is true, because a negative delta H and a positive delta S, mathematically you have a negative minus, or negative and another negative, because a negative delta T times a positive delta S gives us a negative TS. So that value is negative, and then delta H is negative, which means overall your delta G will be negative. Whereas if enthalpy is positive, entropy is negative, negative temperature times a negative entropy is going to be a positive, so your delta G is going to be positive mathematically speaking. So what this means is if your delta S and your delta H, if delta S is positive and delta H is negative, Gibbs free energy is always negative, always. If your enthalpy is positive and your entropy is negative, delta G is always going to be positive or non-spontaneous. What if we have them kind of in the middle? Okay, let's look at this mathematically. So if your enthalpy value is positive, that predicts non-spontaneity. But we can still have a spontaneous system if your delta S is positive and your temperature is high. Because if your temperature is high, that means the right side of the equation is going to be big, and we can essentially ignore the contribution of enthalpy. Because if enthalpy is very, very small, who cares if it's positive? If it's really small in relationship to my temperature times my entropy, then I'm going to have a negative system overall. So at high temperatures, even if we have a positive enthalpy, we'll still have overall spontaneity. And then the same is true, so at low temperatures, if we've got low temperatures, then that right side of the equation is going to be small. That means you're going to have a very small negative T delta S, but you're going to have a large delta H. That means your delta G is going to be positive or non-spontaneous. So what this means is if your enthalpy is positive and therefore suggesting non-spontaneity, your entropy can still overcome that lack of spontaneity from your enthalpy and produce a high negative delta G. Okay, and then the opposite's true when we look at it the opposite way. So if we look at negative delta S's, those are going to predict non-spontaneity, whereas your negative delta H predicts spontaneity. And so if we've got low temperatures, at low temperatures that term is disappearing and your delta H is going to help predict a spontaneous delta G. Whereas if it's at high temperatures, then your entropy term is going to dominate. So it's going to dominate. A negative times a negative gives me a positive or a non-spontaneous reaction. Table 17.5 sums it up very well. If you have a positive delta S and a negative delta H, it's going to be spontaneous at all temperatures. Your delta G is always spontaneous. If your delta S is negative and your delta H is positive, it's not spontaneous at any temperature. And then for the middle, where your entropy says, hey, I should be spontaneous, and your enthalpy says no, or when they're at odds against each other, it's going to be temperature dependent. And so that's going to depend mathematically on which one's going to dominate based on if you're at high temperatures or low temperatures. Because at high temperatures, your entropy dominates, and at low temperatures, your enthalpy dominates. And so there are lots of combinations that you can have for entropy and enthalpy that can help you determine whether or not your Gibbs free energy is going to be positive or negative, and therefore whether or not the system is going to be spontaneous.